Hello, my name is Edward, and I am joined here today with Arnell, and we are presenting to you our data science project, which is called What Makes a Video Game Great? An analysis of video game ratings by genre, platform, and release trends. So, first, we'll start off with what is our project about, and why do we even pick video games as a topic? Well, first of all, we love video games. Second of all, unrelated to the study, also a fun fact, playing video games, and I quote, can help surgeons improve surgical skills, including fine motor control, reaction time, and decision making process. Quoted by Science ABC. Now, we believe that video games play a significant role and influence in today's society. And so we want to study about video games. Particularly, we want to identify factors that contribute to high scores for video games across different platforms and genres. That is our problem statement. We also have a few objectives of our project, and that is to understand the characteristics of highly rated games by genre, platform, and release trends. We also want to provide actionable insights for stakeholders, developers, and gamers. I myself am a gamer. So we have three data science questions in which we've cultivated that are answered by this project. Number one, which genres receive the highest ratings? Number two, how do platforms influence ratings? And number three, what trends are visible in game ratings over time? So our data science project will be split into 5 portions: data gathering, cleansing of data, exploratory data analysis, modeling, and evaluation. I will be covering cleansing data and exploratory data analysis, while Arnell covers data gathering and modeling. Me and Arnell will both cover evaluation. Now, for data gathering, I would like to pass the mic on to Arnell.
Hello, everyone. Today I'll be discussing the data gathering process for our analysis of video game ratings. To begin with, we selected a dataset from Kaggle titled IGN Games from Best to Worst. This dataset is particularly valuable because it provides comprehensive information about video games released until 2015, including essential columns such as title, score, platform, genre, and release date. The dataset was sourced from IGN, a reputable video game and entertainment media website, ensuring that the data is both accurate and reliable. We utilize Kaggle's API to download the dataset, which guarantees that we have the latest version available. Now, let's take a closer look at the coding aspect of our data gathering process. In the first line, we imported the necessary libraries, specifically Kaggle Hub and Pandas. The Pandas library is a powerful tool for data manipulation and analysis, and Kaggle Hub provides access to datasets hosted on Kaggle. Next, we used the Kaggle Hub dataset download function to download our dataset. The command includes the specific path to the dataset titled IGN Games from Best to Worst. The download progress is indicated in the terminal, showing a 100% completion status, confirming that we successfully retrieved the entire dataset. Following the download, we read the CSV file into a data frame using the pdread CSV function. This command loads our data into a structured format that we can easily manipulate and analyze. The game head function is then utilized to display the first few entries of the dataset. As we can see, the data frame comprises crucial columns such as title, score, score praise, platform, genre, release year, month, and day. This gives us a glimpse of the data we have and indicates that we have a total of 18,625 entries to work with. Additionally, we check the dataset's information using game info. This function reveals the structure of the data frame, including the number of entries and the types of data within each column. Notably, we see that the score column is a float, while the rest of the columns are either integers or objects, providing us with a clear understanding of data types for our analysis.
And now it is time for data cleansing. So, for a meaningful analysis, data cleansing focused on preparing the data set by addressing any missing values, removing duplicates, and ensuring consistent data formatting. So we first checked for any duplicates within the data. About 48 duplicate rows were detected, and of course we had to remove those to remove the or reduce the risk of bias. Then we removed any missing values, and in this case we found 36 entries that were missing values in the genre column. So we chose to remove these rows completely to maintain the data integrity and also to not compromise the overall data set. We also combined release year, release month, and release day into a single release date column, which allows for an easier trend analysis over time. We also decided to split multi-genre entries from the data into individual genres to accurately analyze each genre's impact on the game ratings. Now, upon reviewing the data, we discovered that there were categories with less than 10 entries, such as golf and Sega CD and platforms. Now, we wanted to ensure our analysis represents broader trends without outliers skewing the data. So we applied a proportional threshold, excluding genres and platforms with fewer than 0.5% of the total entries. Now, this approach, we believe, ensures that each category has sufficient number of entries and would maintain a balanced representation of genres and platforms. We also chose to omit the score phrase column, which provides a qualitative assessment of each genre's game score. For example, masterpiece, amazing, poor, and although they are insightful descriptors for each game score, it is categorical in nature, and it's a representation that's derived directly from each game's respective numerical score. So, given that we are focused on the quantitative relationship among genres, platforms, and ratings, we use the score column as the main measure of game quality. Additionally, to track the trend of average game scores over time with a consistent view, we set a minimum threshold of 100 games per year. Now, this filtering, we believe, would exclude years with insufficient data, where individual games could disproportionately affect the yearly average. Next would be our exploratory data analysis. So upon proceeding with the data inspection, we examine each column to understand its data type, contents, and relevance to our analysis. Additionally, our primary question centers around patterns across categories and trends over time rather than correlation. Therefore, we also opted to focus on the descriptive statistics and visual exploration. For our feature extraction process, we identified key variables that align with our data science questions about game ratings, and we chose the following features for analysis. One is score. This is our main measure of game quality, which is our target variable. Second is genre, which is a categorical feature, which helps identify high performing game types, such as, for example, RPG, adventure, shooter, you name it. Three would be platform, which is another categorical feature, which helps identify which platforms have higher rated games, which potentially indicate differences in user experiences or platform strengths. We have, for example, PlayStation, Xbox, PC, those are some examples. And lastly, we also have release date, a transformed single date feature, which facilitates our exploration of trend ratings over time. And for our data visualization and variable importance, first we have the distribution of game scores. This provides context on what are considered high or low in scoring, framing our analysis for top performing genres and platforms. Next, we have average score by genre. So this visualization addresses our first question regarding which genres tend to receive higher ratings. We also have average score by platform, which directly answers our question regarding platform influence on ratings and may provide platform specific strengths. And lastly, we also have average score over years. So this visualization answers our third question, aiding us to see how average ratings over time or how average ratings have evolved throughout the years. So here's our first lines of code for exploratory data analysis. As you can see, as I've mentioned before, the distribution of game scores. Games are rated between 6 to 9. We also calculated the average scores of genre and platform. And as you can see here, here's some sample. Uh, RPG so far has the highest rating, and we also see that PlayStation 4 also has the highest rating, average rating as of right now. And here's some more lines of code. We presented the uh, top 15 genres by average score and top 15 platforms by average score. If you notice, the y-axis, which is the average score, it's between 6 to 8. The reason why we did that was because we are able to better see the differences in ranking between these genres and platforms. So that's just a choice we made. We also decided to include z-score analysis to contextualize each genre's and platform's average score by comparing its deviation from the overall mean of scores in terms of standard deviation. And we believe that this metric aids in revealing which platforms and genres perform better or worse compared to the general score of distribution. And a positive Z score would suggest a strong performance that is above the overall average, while a lower or negative Z score would suggest a weaker performance that is below the overall average. And this could assist in showing insights that could suggest a correlation between certain genres or platforms. And as you can see right here, there are genres such as RPG, strategy, and platformers that are visually highlighted to score above average. And for platforms, we have PlayStation 4, iPad, and Xbox One, rating supreme for for the average game score. And now, lastly, for our exploratory data analysis, is the inclusion of the average game score over years. So here we have a visual representation in the form of a line graph that shows the average game score over the years. As you can see right here, it rises from 1995 up to 1997. It stagnates around there. It peaks at around 2002, and then as we can see right here, there's a sharp decrease in game quality toward the 2008 Great Recession. Now we could view it both ways, right? The Great Recession could have happened because game quality decreased, right? Well, not necessarily. Game quality might have decreased in 2008 because it was the recession, but as we can see after 2008, there's a sharp upward increase in trend of average game score over the years, which is amazing. As you can see right here, from 2008 all the way up to 2015, it's just a steep increase of average game score. So video game quality must have spectacularly rose from 2008 onwards, which is amazing. On a personal note and a personal bias, I believe that these were the best years of gaming around 2010 to 2015. These were absolute peak, in my opinion, of course, which is separate from this data analysis, of course. Now, for modeling, I would again want to pass the mic to Arnell.
Now, let's discuss the modeling phase of our project, focusing on the selected features and their rationale for our analysis. We identified several key features for our modeling process that align closely with our data science questions. These features are essential for uncovering insights into how genres, platforms, and trends influence game ratings. First is cluster. This feature was generated from the k-means clustering model. It represents the grouping of games based on similar score ranges, categorizing them as highly rated, average rated, or lower rated. Integrating this feature into our decision tree model allows us to leverage the natural segmentation within the data, enhancing our ability to classify games accurately. Second is release date. The release date is a crucial component because it can significantly influence ratings. Factors such as technological advancements, evolving gaming trends, and even platforms shifts play a role in how newer games are perceived and rated. For instance, more recent games might score higher because they benefit from improved graphics and gameplay mechanics, contending with earlier titles that lack those advancements. Third is genre. This feature highlights the idea that certain genres consistently receive higher or lower ratings. Each genre has different distribution patterns for ratings, influenced by audience preferences and industry standards. Understanding which genres excel can provide insight into market trends and player satisfaction. Lastly, we considered the platform as a strategic variable. Different platforms might yield varying ratings due to factors like performance differences, exclusivity, and the size of the user base. By evaluating which platforms are associated with higher rated games, we can draw connections to player experiences and platform capabilities. So these selected features not only address our specific data science questions, but also help us interpret how different elements contribute to game ratings over time. By focusing on these variables, we aim to uncover meaningful patterns and make informed predictions about high rated games based on past data. This approach allows us to answer questions such as which genres receive the highest ratings, how platforms influence ratings, and what trends emerge over time. So, the thoughtful selection of these features enables us to deepen our analysis and draw actionable insights into the gaming industry. Now, let's dive into model training, testing, and process, highlighting the two models we implemented, the K means clustering model and the decision tree classification model. First, we started with the K means clustering model. This model was used to categorize games into broad performance categories based on their ratings. We focused on three main groups: highly rated games, rated games, and lower rated games. This clustering helps us understand the distribution of ratings across different games and provides essential context for our subsequent analysis with the decision tree model. To optimize our clustering, the dataset was standardized, ensuring that all features contributed equally. We determined the optimal number of clusters using the elbow method, which indicated that three clusters were the most effective. This step was crucial because K-means is an unsupervised learning approach, and it allowed us to identify meaningful patterns in the data without predefined labels. Next, we employed the decision tree classification model. This model was designated to classify games into a specific rating categories based on selected features, including cluster, release date, genre, and platform. We split our data set into a training set, 70%, and a testing set, 30%, using the train test split function. This split ensures that we can fairly evaluate the model's performance. The model was trained with the training set, using the rating category as the target variable. This enables us to predict the rating based on the game's attributes. After training, we evaluated the model's performance on the testing set to assess its accuracy and general, generalizability. The use of these models allowed us to uncover insights into game ratings and the factors influencing them. The K-means clustering provided us with a foundational understanding of rating distributions, while the decision tree enabled us to make specific predictions based on key features. And together, these approaches contribute significantly to addressing our data science questions and enhancing our understanding of of the gaming landscape. Now, let's take a moment to discuss the required libraries that facilitated our modeling process. Each of these libraries plays a crucial role in data manipulation, numerical operations, and evaluation. First is Pandas. This library is essential for data manipulation and processing. It allows us to read, clean, and structure our data sets effectively, making it easier to analyze and visualize the data. Second is NumPy. We, we relied on NumPy for numerical operations, particularly for standardizing our data. This library provides support for large multidimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays. Third is scikit-learn. This is one of the most comprehensive libraries for machine learning in Python. It includes several vital functions. K-means for clustering to group games based on their ratings. Decision tree classifier for creating our classification model. Train set split for dividing our data into training and testing sets, allowing us to evaluate model performance accurately. Classification report and matrix for assessing the model's accuracy and other evaluation metrics. Standard scaler for scaling our data before applying the clustering algorithm, ensuring that each feature contributes equally to the outcome. Fourth is matplotlib and seaborn. This, these visualization libraries were instrumental for our analysis. We use matplotlib for basic plotting and seaborn to create informative and aesthetically pleasing visualization. These tools help us represent distribution, feature importance, and the confusion matrix, enhancing our ability to interpret the results visually. By leveraging these libraries, we ensured a robust and efficient modeling process, enabling us to answer our key data science questions effectively while maintaining clarity and accuracy in our analysis. Now let's dive into our k-means clustering analysis, which is a key component of our project. On the left side of the slide, we see the code used to implement the k-means clustering model. We start by importing essential libraries. The standard scaler is employed to standardize the score column, ensuring all numerical features have a mean of 0 and a variance of 1. The one-hot encoder is used to convert categorical features, specifically platform and genre, into a format suitable for our model. Here, we define a column transformer. This allows us to apply different transformations to the numerical and categorical features simultaneously. The score is scaled, while platform and genre are one hot coded. Next, we create a pipeline that first applies our pre-processing steps and then runs the k-means clustering, initially assuming 3 clusters. This will help us streamline our workflow. We fit this pipeline to our filtered dataset, allowing the k-means model to learn the structure of our game data based on the pre-processed features. And to find the optimal numbers of clusters, we implement the elbow method. We iterate through a range of cluster numbers from 1 to 10, fitting the k-means model each time and calculating the sum of squared errors SSE, which measures how tightly grouped the clusters are. And finally, we plot the SSE against the number of clusters. The resulting curve helps us visualize where adding more clusters ceases to significantly improve the clustering. On the right side, we see the elbow method's result. The x-axis represents the number of clusters, while the y-axis shows the SSE. As we increase the number of clusters, we observed a decreasing trend in SSE, indicating better clustering. However, there's a distinct elbow point around k equal 3, where the rate of decrease sharply slows down. So, this analysis suggests that 3 clusters are optimal for our dataset. This finding allows us to effectively categorize games into meaningful clusters, enhancing our understanding of how different features relate to game ratings. Overall, the k-means clustering model helps us uncover valuable insights into the structure of our video game dataset. Now let's take a closer look at the results of our k-means clustering analysis after determining that 3 clusters were optimal. This part of the analysis helps us understand how video games are grouped based on their scores, platforms, and genres. Moving over to the code on this slide, I'll explain each section and what it accomplishes. Here, we initialize the k-means model as specifying three clusters. We also set a random state for reproducibility and create a pipeline that includes our pre-processing steps followed by k-means clustering. Next, we feed the pipeline to our filtered dataset, which ensures that our model learns to categorize the games based on the processed features. After feeding the model, we, we retrieve the cluster labels assigned by k-means and add them as a new column to our game filtered data frame. This allows us to see which games belong to which cluster. To get a quick view of the cluster data, we print the first few entries from our data frame, displaying the score, platform, genre, and the corresponding cluster assignment. Within loop, through each cluster, printing out the descriptive statistics for each one. This gives us insights into the characteristics of the games within each cluster. Examining the output for each cluster, we can draw some key insights. First is cluster 0. The first cluster contains 7,191 games with an average score of approximately 6.57 and a standard deviation of 0.60. This indicates a fairly consistent range of scores. The scores within this cluster range from a minimum of 3.5 to a maximum of 7.7, suggesting a variety of quality. Games in this cluster tend to be from multiple platforms, indicating broad appeal, with predominant genres possibly being action and RPG. Cluster 1. This cluster includes 3,416 games with a lower average score of around 4.07 and a higher standard deviation of 0.99. The scores here are more varied, ranging from zero point 0.5 at the lowest to 5.3 at the highest. This suggests that games in this cluster may not perform as well overall, often associated with platforms like the PSP and PS2. The distribution indicates that these older systems might be linked to less favorable ratings. Finally, we have Cluster 2, which comprises 9,463 games and boasts the highest average score of 8.37. The standard deviation here is 0.58, indicating that these high scores are relatively consistent across the games. Scores in this cluster range from a minimum of 8 to a maximum of 10, predominantly featuring games on more recent platforms such as the Xbox 360 and genres like adventure. These results highlight not only how games are clustered but also the factors influencing their ratings. For example, the highest performance tends to cluster around certain platforms and genres, indicating that focusing development efforts in these areas could potentially enhance future game ratings. By understanding these clusters, developers and stakeholders can better navigate market trends and address player preferences. Next, we'll explore the visualization that help us understand the k-means clustering results more effectively. We'll be focusing on the distribution of game scores across clusters, as well as analyzing the genre and platform distribution within each clusters. We begin by importing the necessary libraries, Seaborn for data visualization and Matplotlib for creating plots. This segment creates a box plot to compare the score distribution across the clusters. The box plot visually summarizes the distribution of scores for each cluster, showing us the median, quartiles, and potential outliers. Here, we create a bar plot to illustrate the distribution of game genres within each cluster. The count of each genre is shown, differentiated by cluster, providing insights into what types of games dominate each category. Finally, we generate a bar plot for the platform distribution across clusters, allowing us to see which platforms are most represented in each cluster. Here in this result, we observe distinct patterns. Cluster 0 shows a high median score around 6.5, while Cluster 1 has a much lower median around 3.5, indicating much poorer performance. Cluster 2 appears to also show up towards the higher end of the scoring distribution. Here, it's clear that certain genres like action significantly dominate Cluster 0, while the presence of different genres within Cluster 1 seems limited. This suggests that games in this cluster might not align as well with popular genres. The platform distribution by cluster reflects trends where platforms like PC, PlayStation 2, and Xbox 360 have notable counts in specific clusters. Knowing which platforms coincide with higher rated games helps us understand market preferences. Now, here we analyze the score distribution by cluster. Cluster 0 is characterized by a moderate score range between 6 and 8, which likely represents average rated video games. This cluster indicates that these games perform reasonably well but are not necessarily standout titles. Cluster 1, on the other hand, shows a lower score distribution around 4. This cluster likely includes low rated video games, which may represent genres or platforms that didn't resonate with players or lack market popularity. Finally, Cluster 2 boasts the highest scores, ranging between 8 and 10. This suggests that it contains high rated video games, pointing to titles that have excelled in quality and player reception. Now, here focuses on genre distribution by cluster. In Cluster 0, genres like action, sports, and adventure dominate. These genres typically feature a diverse range of games. While some excel, many fall into the average category, hence the moderate overall ratings. Cluster 1 indicates genres such as action and adventure as well. However, the titles in this cluster are likely of lower quality, often consisting of obscure games that did not perform well. Moving to Cluster 2, we find that RPGs and strategy games are predominant. These genres often incorporate strong storytelling and depth, aligning well with the high ratings this cluster receives. And finally, we examine the platform distribution by cluster. Cluster 0 features platforms like PC, PlayStation 2, and Xbox 360, which is expected as these are popular and host a mix of mid level games. Cluster 1 also includes PC and PlayStation 2, showing that these platforms support a variety of titles, but notably, many are of lower quality, which contributes to the overall lower ratings in this cluster. Lastly, Cluster 2 highlights PC as a significant player, suggesting it hosts many high quality games. Additionally, platforms like PlayStation 4 and iPad are present, indicating that they too offer a selection of well rated games. Now, I will walk you through the code and results from our classification model, specifically focusing on how we categorize game ratings into different categories: high, medium, and low. We start by defining a function, categorize rating, which assigns a category based on the game score. Scores below 5 are classified as low, scores between 5 and 7 as medium, and scores above 7 as high. This categorization is crucial for our classification model. Next, game filtered. We apply this function to our data frame, adding a new column rating category, which holds the category for each game. This transformed data will be used for training our model. We then perform one-hot encoding on the categorical features, genre, and platform to convert them into numerical form, making them suitable for the decision tree classifier. Next is the game encoded drop. Here we separate our features x from our target variable y, which is the newly created rating category column. Non-numeric columns are dropped to prepare the data for modeling. We then split the data into training and testing sets, allocating 70% for training and 30% for testing the model's performance. Next is a decision tree classifier is initialized and trained using our training data. Decision trees are effective for classification tasks due to their ability to model complex relationships. Now, after training, we predict the categories for our test set and calculate the accuracy of the model in this. In this case, we achieved an accuracy of approximately 79%. Additionally, we generate a classification report that provides precision, recall, and F1 score metrics for each category. The report indicates that the model performs best for the high category with a precision of 0.87 and an F1 score of 0.88. The results from this classification model demonstrate promising accuracy and highlight the model's ability to distinguish between different rating categories effectively. And by analyzing precision and recall for each category, we can make informed decision to improve our game ratings prediction model further. In this slide, we we visualize the importance of features used in our decision tree model. We first extract the feature importances from our trained classifier. These values indicate how much each feature contributes to the model's predictions. Next, we create a data frame that pairs each feature with its corresponding importance value, setting the stage for visualization. We sort the features by importance, focusing on the top four. The bar plot clearly illustrates what the most significant feature in our model is cluster, followed by release day, release month, and release year. This indicates that these temporal and categorical features play a critical role in influencing the game's rating. And here in this slide showcases a visual representation of our decision tree with limited depth. Using the plot tree function, we create a diagram illustrating how our decision tree makes predictions. This visualization has a max depth of 1, which keeps the tree simple for better understanding. The tree starts by splitting on the cluster feature, showing how it divides the dataset into two branches based on that feature. Each subsequent node further subdivides the data based on conditions from other features like release month and platform. This layout allows us to see how the model navigates through the features to arrive at its class predictions. In this final slide, we present the confusion matrix for our decision tree model, which offers insights into its classification performance. First, we generate predictions on our test dataset using the trained model. Next, we compute the confusion matrix, which compares the actual labels against the predicted labels. Third, the heat map visualizes the confusion matrix, highlighting how many instances of each class were correctly or incorrectly classified. For example, we see that the model correctly identified 3,283 instances of high ratings, while it's misclassified 404 instances as medium. This allows us to quickly assess the model's strengths and weaknesses, Understanding the areas of misclassification will help refine the model further for improved accuracy. Overall, the combination of feature importance, tree structure, visualization, and confusion matrix provides comprehensive insights into how the decision tree classifier operates and its effectiveness at classifying game ratings. On the next slide, we will discuss the evaluation phase of our model. To start our evaluation, let's recap the main objectives of our project. We aim to identify factors that contribute to high ratings in video games, focusing on different platforms and genres. Specifically, we set out to answer three data science questions. First is which genres consistently receive the highest ratings and what patterns can be observed across these genres. Second, how do gaming platforms influence average ratings, and are certain platforms associated with higher rated games? Third, what trends can be observed in video game ratings over time, and has there been an improvement in average scores across release years? These questions shaped our analysis and guided our approach. In order to answer our questions, we developed two models. One, the K-means clustering model. This model grouped games into three main clusters: high rated, average rated, and low rated games. By applying this model, we gain insights into how games naturally fall into different rating categories based on inherent patterns in the data. Although it doesn't predict future data, it helps us observe common characteristics within each rating range and identify prevalent genres and platforms in the high rated cluster. Second is decision tree classification model. This model learned patterns to classify games into high, medium, and low rating categories based on selected features. It demonstrated an accuracy of approximately 79% and achieved an F1 score of about 88%. This indicates that it performs well in predicting high rated games. While this model was not purely predictive, it provided valuable insights into which factors were most influential in determining game ratings.
And now for the exciting part, the results of our project. Something that game developers, stakeholders, and gamers want to know. What are the key actionable insights? So we've compiled the following key actionable insights based on our analysis and models, which also answer our data science questions. First of all, first key actionable insights is genres like role playing games and strategy were commonly associated with higher ratings. These genres stood out in high rated clusters, and they consistently received higher scores. These genres benefit from strong narrative element and players assuming the roles of characters in a fictional settings. So RPG games examples. For example, we have Skyrim, Fallout, Monster Hunter, of what else? Genshin Impact, you name it. So these are very popular games. Strategy, we could talk about League of Legends, Dota, Mobile Legends even too. So these are games that are commonly associated with higher ratings. So stakeholders may consider investing in RPG and strategy as these genres appeal to audiences who value an immersive story narrative and complex gameplay. Developers can capitalize on these game genres' strengths by focusing on world building and detailed narratives. Our second key actionable insight is number 2. PC and PlayStation consoles were commonly associated with high ratings. These platforms are well regarded for their high performance capabilities, which allow for an enjoyable visual aesthetic and technically complex game. So, stakeholders may consider focusing their investments on high performing platforms like PlayStation and PCs. I personally, on a personal note, use these platforms, and they're my favorite platforms to use and play on. They have shown consistent trend in hosting high rated games. Further investments to these platforms can yield higher returns as they support genres and gameplay quality that align well with user experience and expectations. Game developers, on the other hand, may consider focusing on creating complex gameplay with detailed graphics and high quality narratives. RPG and strategy games perform well both on PC and PlayStation platforms because because of their high performance capabilities and platform flexibility. And now for our third and last key actionable insight. Number 3, average game scores are shown to generally improve from 2007 onwards, which may correlate with the advancements in accessibility technology, graphics, and gameplay mechanics. As I mentioned before, this was around the time after the Great Recession, the 2008 Great Recession. So newer console generations and improved game development. So this finding suggests that games released in more recent years tend to receive higher ratings, likely due to improvements in game quality, user expectations, and of course the technological advancements and game developing advancements. So users can generally expect as years go by, games would get better because technology also gets better. So the trend of improving ratings over time indicates that newer technology, both in hardware and development tools, has raised player expectations, which makes sense. If gamers are satisfied with a game from last year, they're expecting something greater each year and next year, right? So stakeholders should invest in games timed with major hardware releases, and developers should focus on quality, particularly for popular genres, to meet the high standards associated with recent releases.
Our exploratory data analysis revealed significant insights. For genres, we identified RPG, strategy, and platformer as the top genres based on average scores. While all these genres generally perform well, RPG and strategy games consistently rank higher in the clustering model, suggesting that they dominate the high rated clusters across various platforms and release years. For platforms, we found that while newer platforms often yield higher average scores, older consoles like PlayStation 2 and Xbox 360 frequently appear in high rated clusters. This suggests that older platforms maintain their relevance by hosting a variety of high quality games, highlighting their versatility over time. And overall, these additional insights align with our initial observations, confirming that RPG and strategy games are among the highest rated genres, with both PC and various PlayStation platforms acting as strong performers. So on this slide, we have two visualizations. The left graph shows the top 15 genres by average score, clearly reflecting how RPG, strategy, and platformer genres dominate the rankings. The right graph presents the genre distribution by cluster, allowing us to see the count of games in each genre across the different clusters. This distribution emphasizes how certain genres are more common in the high rated cluster compared to others. And this slide features two key visualizations focused on gaming platforms. The left graph illustrates the top 15 platforms by average score, with PlayStation 4 and iPad showcasing high ratings. On the right, we observe the platform distribution by cluster, highlighting which consoles commonly appear in high rated clusters. Notably, older platforms like PlayStation 2 is still rank well, reinforcing the insight that both older and newer platforms contribute to high quality game experiences. In this slide, we analyze trends in average game scores over the years. The graph illustrates the fluctuations in average scores from 1995 to 2015, re- revealing a general upward trend. Notably, we see increased average ratings in the later years, indicating an improvement in game quality over time. This upward trajectory correlates with advancements in technology and game design, suggesting that the gaming industry continues to evolve positively.
And now for our recommendations and suggestions for this study. So, one suggestion and recommendation that me and Arnell believe that should be done in future studies is to extend the data set. So the games that we've included were only up until 2015, and today it is 2024. So we suggest including games that are released up until 2024 or 2023 to capture recent trends and preferences, because it may be different now between 2015 and today, right? So game scores might have fluctuated, it might have gone down. We don't know. We also suggest adding a monthly release date to identify seasonal patterns in high rated game releases. So it could better predict perhaps when games should be released and their association with correlation with higher game scores. We also believe that future studies should explore additional classifiers and algorithms. So other test models like random forests, support vector machines, and gradient boosting for improved prediction accuracy, and also consider time series analysis for forecast future game rating trends. And lastly, we also suggest to refine the clustering model. So experiment with different values of k for better segmentation. Try a uh, hierarchical clustering to reveal multi-level structures and genres and platforms, helping identify niche subclusters for targeted development.
As we wrap up our presentation, I want to take a moment to acknowledge the resources that contributed to our project. This slide highlights our primary data source from Kaggle, which provided the comprehensive data set for video game ratings we analyzed. Additionally, we utilize several libraries in Google Colab, such as Pandas and Scikit-learn, for our data processing and model development. We also drew upon various research articles that inform our approach and deepened our understanding of the gaming industry, player preferences, and the significance of trends in ratings. Each reference listed here has played a crucial role in shaping our analysis and supporting our conclusions. So, thank you for your attention throughout this presentation. Edward and I hope our findings have provided valuable insights into the factors affecting video game ratings. We are now happy to answer any questions you may have.
All right, and that is the end of our presentation. We hope it was very informative, and also please check the second video for the notebook being run just to prove that it works. And thank you again. My name is Edward, and with me is Arnell. Have a good day.